This video we're going to prove some very important basic facts in group theory. If G is a group, then the identity element is unique. That is, there's just one of them. For every element A in the group G, it has exactly one inverse in G. That is, the inverse is unique. And A inverse inverse, or the inverse of A inverse, is A. And the inverse of AB is B inverse times A inverse. Before we get into proving these four facts, let me ask you nice folks to subscribe to my channel, especially if you like watching proofs of mathematical facts like this, and limits, and corollaries, etc. This should be a really interesting YouTube channel for you to subscribe to. Okay, so we want to show that their identity element is unique. So proof of A. Suppose G has two identity elements. Call them E and E prime. Let A be, well, you know what, we don't even need to do that. Thinking of E as the identity element, E times E prime is E prime, because we're thinking of E as the identity element. That is, this element times anything gives back to anything. Now, thinking of E's prime as the identity element, E times E prime is E. Because if this is the identity element, any element times the identity should give you back that same element. Now, putting this together, we have it. E is equal to E times E inverse. I got that from here. But from up here, it also equals E prime. That is, E equals E prime. We did it. Proof of A is done. B, I want to show that every element has a unique inverse. So we suppose otherwise. Proof of B. Suppose that A prime and A to the minus 1, I'm going to call it A inverse though. A prime and A inverse are both inverses of A. Now, what's the best way to write this? Okay, we know that A prime is equal to A prime is equal to A prime times E, which is A prime times any old way of writing E. Well, A times A inverse is E, but that's the same as A prime times A inverse. But A prime times A is E. This is E times A inverse, which is A inverse. Therefore, A prime is equal to A inverse. That is, the inverses are unique. Part C, I want to show the following. Proof for C. I want to show that A inverse inverse equals A. Okay, now, I don't care at all what's in there. In fact, let's make believe I covered it up. You can't see it. Well, if what's in here is really the inverse of A, that would mean this times this is the identity. The only way what's in here is the inverse that gives A, or what inverse is A, is if this times this gives you back the identity element. But it does. Okay, this equals A if and only if this element times A is E. But it is. It is. Okay, this is true. That means this is true. Whatever this is, if it's a B inverse is A, that's the same statement as B times A equals E. The only thing is that it wasn't B. Let's not discriminate about how something looks. Just because it has an inverse doesn't mean that it isn't an ordinary element. Okay, if you multiply these two and you get A, then the inverse of this one, A inverse inverse, is A. Okay, so that proof was just by checking. Just like D is going to be by checking. We want to show the following, that AB inverse is B inverse A inverse. This is not part of the proof. Well, maybe it is. If and only if AB times this equals their identity. But let's look at this more carefully. AB times BA, B inverse A inverse, B inverse A inverse. This is the same as AB times B inverse times A inverse, just the associative law. Now, I'm going to use the associative law in the brackets. That's A times B inverse times A inverse on the outside. That's A times Z times A inverse. But A times Z is A. That's A times A inverse. We get E. So yeah. Since this is true, then this is true. That completes this lemma. Proved all 4 facts, probably in just a couple of minutes. If you like watching math like this, subscribe to my channel, click the like button. See you guys in the next video. Never forget, watch and learn.